Hello everyone, I'm Dr. Jyoti Mandala. Welcome you all to the video lecture series on the course operating system. We are learning about the deadlock concept. In our last lecture, we understood about what is deadlock and how was one simple example we have understood where the system has led to the deadlock. And also we understood the first way of finding whether a system is in deadlock or not. So we have understood in our last video, this is the first approach where using these four necessary conditions, if these four conditions occur simultaneously, then the system may lead to deadlock. But of all these four, we understood like the first of one, which is mutual exclusion, is difficult to remove. So if you could able to remove hold and wait, no preemption and circular wait, we may avoid the system to enter into a deadlock situation. Okay, in today's lecture, we will understand the second way of understanding whether our system is in deadlock or not, that is through resource allocation graph. So keep your heading all of you. The second way of finding whether a system is in our system is in a deadlock or not, which is through resource allocation graph. Now, what is this graph? You already know a graph will be represented with G. Let us consider a graph has been represented with the G, and G will be having a set of vertices and set of edges. So a graph is a collection of vertices and edges. Right. Now, in our resource allocation graph, V is nothing but vertices, where V is nothing but it is having processes. Your vertices are your processes and your resources. All your processes and resources are your vertices. Okay, processes will be represented with circle and resources will be represented with a square. Now, in the square, we will have some dots represented. The dot is nothing but one dot represents one instance. So, the number of dots you have, that many number of instances you have. Suppose if you have one dot, you have one instance of your resource. One instance means one copy. Let us consider you have resource printer. If you have one dot, then you nothing but you have one printer only. Suppose if you want to have two printers, then you need to represent with two dots. That means two dots is nothing but that many instances. So dot represents the instances of the resources. Got it? So your vertices are your processes and resources. Now coming to edges. Edges are your two types of edges are there. First type is your request edge. A request edge is nothing but when a process wants to have any resource. Suppose if a process wants resource Ri, if Pi process wants resource Ri, then the edge will be from Pi to Ri, where Pi is requesting Ri. Second type of edge in our graph may be your allocation edge, which is also called as assignment edge. Okay. This will be like if a resource has been assigned to a process Pi, then there will be an edge from Ri to Pi. So this is your requesting edge and this will be your allocation edge and these are your vertices. Having these things in our mind, if you can able to construct one graph, by seeing that graph, we can tell whether our system is in deadlock state or not. Okay, so let us see multiple cases here. Okay, with this basic background, let us see multiple cases. The first case is after drawing the resource allocation graph, where you will have vertices and edges, and you will be connecting as per their request and as per their allocation. You will be having some graph. Okay, now by seeing that graph, let us see the first case. What is the first case? Is case one. If in your resource allocation graph, there is no cycle, then it is nothing but there is no deadlock. I will take one example and let us see one resource allocation graph. And by seeing that, we will understand whether how this is reflecting this case. Okay. See this graph. In this graph, this is one resource allocation graph where we have some processes P1, P2, P3 and the resources R1, R2, R, R1, R2, R3, R4. Observe here that this R2 is having two instances, R4 is having three instances, and R1 is having one, and R3 is having one. Understand the terminology here. The edge between P1 and R1 is called as a request edge, and the edge between R2 and P1 is called as an allocation edge. Observe here two instances are there. One instance is under the control of P1, another instance is under the control of P2. And we have only one instance of R3 which is under the control of P3. So depending upon your request allocation, we have to draw the edges and we have to come with one graph which is called as a resource allocation graph. Now, once you have done with your resource allocation graph, you need to observe for any cycle if it is forming or not. Observe here, is there any cycle forming? Cycle is nothing but from here to here, from here to here, from here to here, and again from here to here. But here the arrow mark is different. So there is no cycle here. And one more cycle from here to here, from here to here, from here to here. After this, it is not going and requesting and holding anything. So there is no cycle here. That means in this graph, there is no cycle. So if there is no cycle, the first case tells there is no deadlock in our system. I hope you all are clear with this first case. What is the first case? If there is no cycle, there is no deadlock. Okay, let us move to the second case. Second case, it will be having two options. Second case is if there is a cycle. First case is if there is no cycle. But in the second case, if there is a cycle, we have two options. The first option is if the resources are of single instance. Okay. Or if the resources are of multiple instance. B option is resource or of multiple instance. Okay, if let us see resources of single instance. Okay, resource of single instance is nothing but our system will be having only one resource. Okay, got it? And that resource will be assigned to the requested process. Okay, so let us consider this scenario. Observe this scenario. What happened here? We have resource R1 which is of only one instance and resource R2 of only one instance. Now we have got this resource allocation graph where P1 is holding R1 and it is requesting for R2 and P2 is holding R2 and requesting for R1. Did you observe here there is a cycle? There is a cycle here. So if there is a cycle, obviously that is a second case. But if the instances are of single instance only, then it will lead to deadlock. It will lead to deadlock. That means this example, we are having the deadlock situation. Got it? In this scenario, in this example, this is not leading to any deadlock there as there is no cycle, right? But if there is a cycle, then we need to check it is a single instance or a multiple instance. If this is a single instance, it will lead to deadlock. So this situation has led to deadlock. But if the resources are of multiple instance, then it may or may not lead to deadlock. Okay. So if it is, how that will be? Take this example. This example you see the first case where there is a cycle. Observe here how there is a cycle. You see the cycle is from here to here, from P1 to R1. Okay. From P and then P2, R3, P3 and did you see here there is a cycle. So there is a cycle formed here. But if this is a cycle formed here, whether it is leading to deadlock or not, yes, it will lead to deadlock. Why? Because the instances are multiple instances. Observe here, two instances are there. This one is under the control of this one and this one is under the control of P2. Now, P3 requires R2. But P3, when it gets R2, only if it is released by P1 or P2. When P1 will release R2 if it gets R1. But when it gets R1, when it is released by P2. But when P2 releases this one, if it gets R3, but R3 is under the control of P3. But P3 when it completes only if it gets this R2. So there is a cycle and multiple instances are there, and this is leading to deadlock. Okay, if multiple instances are there, it is leading to deadlock. But always it may not be the case. Always it may not be the case. In this case, if there is a cycle and multiple instances are there, there may be situations where it may not to lead to deadlock also. For that, understand this diagram. This diagram you see. What is happening here? You see this diagram. We have process P1 and then multiple instances of R1 and R2 are there. P2 is there, P3 is there. There is a cycle here from here, here, here and here. Multiple instances, cycle is there, but there is no deadlock here. How can we say that there is no deadlock here? Because you see here P1 is holding R2 and it is requesting R1. Okay. And then R1 when it will get, if P2 completes its execution, P2 is not requesting anything. So it can complete its execution. Once its execution is done, it will release R1 and then R1 can be assigned to P1. Very simple. Did you understand? Did you understand here? P2, as it is holding only R1 and it is not requesting anything, it can complete its execution. After completing its execution, it will release R1 and that R1 can be assigned to P1. Then P1 will be having R2 and it will be having R1. It will complete the execution and it will release this one. And then R2 can be assigned to P3 who is requesting that. Did you see? So even though there is a cycle and it is a multiple instances, it is not leading to deadlock. Isn't it or not? So this case where if you have a cycle and you have a single instance, it will obviously lead to deadlock. But if you have a multiple instances, the system may or may not be in a deadlock situation. So this is how by using your resource allocation graph, how the resources are allocated to the process, you need to draw the graph. After drawing the graph, observe these three cases where if there is no cycle, no deadlock will be there. But if there is a cycle, observe the instance type. If it is a single instance, there is a deadlock. And if there is a multiple instance, it may or may not be in a deadlock. I hope you all are clear with this concept of how can we detect our system is in deadlock by using the resource allocation graph. So this will be helping us to detect the system is in deadlock or not. With this, we come to an end of today's lecture. Let us all meet in the next lecture. Until then, thank you all of you.